Hello everyone, in the lecture today we will continue the topic in the design of the highway subgrade structures. Here is the wish list for the subgrade design that we reviewed in the last lecture. We want the subgrade to have sufficient bearing capacity, low deformability, time-independent properties, no susceptibility to environmental change, and good drainage. In our previous structure, we analyzed the impact of the first heel on pavement design. And from the analysis, we found that first heel could actually reduce the strength of the pavement. So in the design of the subgrade structure, we have to put the points listed in this page in the consideration. First, if there are some first susceptible soils on the ground, we need to think about removing them and replacing them with some other materials. Also, installing the sub-drainage system to lower the local groundwater table is an efficient method. With a lower local groundwater table, we are able to prevent the capillary raising effect so that we can maintain certain amount of the moisture contents. Excavation of the soil to first line and place impervious seal, and the provision of insulating layers to prevent the first penetration can also be very effective to prevent the first heave. We are also able to increase the size of the void to inhibit the soil suction so that we can reduce the impact of the capillary rising effect. In addition, we can stabilize the first susceptible soil by eliminating the effect of the soil fines, such as introducing cementitious bonding with Portland cement, bitumen, lime, and fly ash. Finally, increasing the pavement structure layer thickness can also account for the stress reduction. From previous lectures, we also know that moisture contents had a very significant impact to a lot of soil properties. So in the subgrade structure design, it's very important for us to control moisture content to an appropriate level. In general, the moisture control can be realized by controlling compaction and grading. For the compaction control, we will compact the soil into wet of the optimal and maintain the material uniformly. Also, we want to maintain soil with a uniform moisture and compaction so that they can provide the reliable support to the pavement structures. For the control of grading, usually there are some standard procedure. We will first excavate a deep cut on the ground and place expensive soil only at the bottom of the field, and then cross-haul less expensive soil towards top of the subgrade, and finally cross-haul to get a uniform subgrade. Also, during this procedure, we will apply cement or lime to stabilize the expensive soils. So in order to have a better understanding about moisture control in the subgrade design, we first need to know what is moisture and what's the standard procedure of compaction. First, for moisture, the soil moisture is defined as the water that is held in the spaces between the soil particles. And this happens due to the irregular shapes of the soil particles. With these irregular shapes, voids exist among soil particles and they were filled with air and water. The water is applied to determine the moisture. In general, the moisture is measured with moisture contents. We will usually apply the direct method to measure the moisture contents. The gravimetric method is commonly applied. In this method, we will take the soil sample from the desired depth as what we want to do the experiment, and they are weighted, which will be defined as the wet weight. And they will then dried in the oven at 105 degrees in Celsius for 1 day until all the moisture is driven off. After removing from oven, they are cooled slowly to room temperature and weighted again, and that one is called a dry weight. The difference in the weights is the amount of the moisture in the soil. So for the moisture contents is defined as the wet weight minus dry weight over dry weight times 100. It actually represents a percentage. Soil compaction is the procedure to place soil in a dense state. We know that due to the irregular shapes of the soil particles, there are a lot of spaces between these particles, and the air and water are filling these spaces. The compaction process is trying to reduce the air voids in the soil, while it does not have any impact on reducing the water contents. This procedure is very similar to soil consolidation. However, in the consolidation process, the water is squeezed out of the soil, which will result in lower water contents. However, the soil compaction will maintain the same water contents. The soil compaction will have several impacts to the soil properties. First, it will increase the strength and bearing capacity, and it's also able to decrease the amount of the undesirable sediment of the structure and increase the stability of the pavement slope. In general, the soil compaction process is applied to increase the shear stress of the subgrade soil. With that, we can gain higher bearing capacity, slope stability, and pavement strength. Also, is applied to reduce the permeability of the soil so that we can prevent the soil's ability to absorb water. In addition, the compaction process can reduce compressibility and control the swelling and shrinking potential of the subgrade soil. There are some general principles of soil compaction. First, this process will only reduce the volume of the voids. The two figures here actually demonstrate the changes of the volume for the soil after the compaction. We can see that the voids between the soil particles will be reduced, and in that sense, the total volume of the soil will be reduced. However, this process will not decrease the volume of the solids or the soil grains. You will observe that the amount of the soil particles will remain the same after compaction. In the summary, by considering three contents of the soil, air, water, and solids, by introducing the soil compaction, we will only reduce the volume of the air. The amount of the water and solids will remain the same. The figure here demonstrates the relationship between dry density, which is a dry unit weight, and the water contents. The two lines in this figure comes from two different compaction efforts. Basically, under a given compaction effort, the dry density could be maximized at one water content, and that water content is defined as OMC, that is optimal moisture content. In addition, we can see that by increasing the compaction effort, the dry density will be larger, while the optimal moisture contents will be reduced. If we apply various compaction efforts to the same soil, we are able to draw various curves to represent the relationship between dry density and water contents. The figure here demonstrates various lines under different compaction efforts. By connecting the maximum dry density in each curve, we can gain one line, which is called the line of optimum. This line is almost parallel to the zero air void line, which is also called the saturation line. Along this zero air void line, there isn't any air existing in the spaces between the particles. In reality, there are a lot of factors affecting the effect of compaction, including water contents, amount of the compaction, type of soil, amount of the compactive energy, method of compaction, thickness of the layers, saturation lines, and so on. In this class, we will not go through more details about these factors. In reality, there are a lot of methods applied for soil compaction in laboratory and field. Basically, for coarse-grained soil, we will use the vibration method, and the fine-grained soil, the kneading method is applied. The table here actually shows more details about the vibration method and kneading method. Here I will introduce one soil compaction method, standard compaction test. This test will be applied for the sample preparation in our lab sessions. In this test, the soil is compacted into a mold in 3 to 5 equal layers, and each layer receives 25 blows of the hammer of standard weight. The energy supplied in this test is 595 kilojoules per meter cube. The volume of the mold is 1000 centimeter cube, and the weight of the hammer is 2.5 kilogram. The height of the drop is set as 300 millimeters. The figure here shows the instrument applied for the test. It has a mold with a collar and several hammers with standard weight. In the standard proctor test, at first we need to mix the soil with a varying amount of the water content so that we can achieve different water content values. Usually we will prepare several samples with different water contents so that we can analyze the impact of the water contents to the soil compaction effect. And then we will apply 25 blows from the rammer dropped from the height of 305 millimeters above the soil. The figure on the left actually demonstrates the distribution of the blows applied to each layer. Once one layer is ready, we will work on the other one, and usually we will need to compact the 3 layers for one sample. With the standard proctor test, we are able to estimate the dry density of the soil. In general, the dry density is estimated from the known wet density and water content. Usually, the standard test is applied for laboratory tests. It's not appropriate for airport or highway pavements. Regarding to the compaction for airport and highway pavements, we have to call the modified proctor test. The table here compares the difference between the standard test and the modified test. In general, the mold size of the two tests are the same, while the dropping height from the modified test is larger. The height will be 457 millimeters. Also, the weight of the hammer is larger as 44.5 Newton. Usually for the modified test, we have 5 layers instead of 3 layers in the standard test. We will apply the same number of the blows for each layer, and the energy applied for the modified test is much higher as 2696 kilojoule per meter cube. The figure here shows some test data about the stiffness and the strength with respect to moisture contents and compaction efforts. The figure on the top shows the stress required to cause 5% strain, which is applied to measure the strength of the soil. Under different moisture contents and compaction efforts, each line will represent one compaction effort. We can see that when the moisture content is less than the optimal value, by increasing the compaction effort, the strength will increase dramatically. While when the moisture content is higher than the optimal value, the strength will almost be the same under different compaction efforts. Similarly, we can check some test data about the relationship between the shrinkage potential of the soil with respect to the water contents and the compaction effort. The figure on the top shows the shrinking potential under different water contents with respect to the 3 different compaction methods. Clearly, we can see that with a higher water contents, the shrinkage potential will be much larger. Now we can summarize the impact of the soil compaction to their properties. First, for the soil density. In general, by increasing the compaction effort, the soil density will be higher. For the soil strength, intuitively we can expect the strength to increase with the compaction energy, and it will be larger at the low water contents than higher water contents. Also, stiffness is another important soil property. We expect that the stiffness increases with the compaction energy when they compacted at the dry optimal, which means the water content is smaller than the optimal water contents. And the stiffness is largely independent of compaction energy when the compacted wetter or the optimal, which means the water content is higher than the optimal moisture content. The stiffness dry or optimal is also substantially larger than when compared to wetter or the optimal. For the permeability, we can see that the permeability of the soil at a constant compactive effort decreases when we increase the water contents, and usually it will reach a minimum value at the optimal moisture content. Finally, the swelling of the compacted clay is greater when the compacted dry of the optimal. Here I summarize some comments for soil compaction. First, the purpose of compaction is not for higher soil density. Instead, it's applied to enhance the properties of the soil for a long time. Usually, denser soil is not always better for the pavement design. Second, the soil compaction is usually designed based on the swelling potential of the soil and the required density for the pavement. Usually in the reality, the soil is compacted a little bit wetter of the optimal, which means the water contents should be a little bit higher than the optimal content. If we do the compaction at the dry of optimal, then in the long term, the water is sucked in and it will induce a lot of swelling potentials for the soil. For the subgrade design, we usually introduce a cut and a refill to handle the expensive soil. The cut will usually cause the rebound in the long term, while the refill will generate a settlement in the long term. Both of them are caused by the changes of the moisture content and the suction of water. If we want to introduce some stabilization of the expensive soil with cement and lime, then the inappropriate design may induce some shrink cracks for the road. From the previous analysis, we can see that water in the soil plays a very important role in the pavement design. It's also able to generate various discharges for pavement structures. In general, water reduces the stiffness and shear strength of the soil and increases the deformation for subgrade. And due to the unstable subgrades, the flexible pavement will usually have increased rotting and fatigue cracking. For a rigid model, the water will cause mud pumping and fatigue cracking. Mud pumping might be the most common discharge of rigid pavement caused by the water in the subgrade soil. The three figures on the right shows how the mud pumping is generated. Basically, with the unloaded PCC pavement, there are some free water under the slabs. Once there is a vehicle passing through the crack on the rigid pavement, the free water behind the pavement will be pushed forward and backward and squeezed out of the cracks. In that sense, the mud pumping is generated. Moreover, we can see that when one vehicle is passing through the joint of two PCC slabs, the water behind the slab will be pushed forward and backwards and is mixed with the fine materials behind. Then the mixed slurry will be squeezed out of the surface and create some cavity behind the slab, and this cavity will further induce crackings for the rigid pavement. In reality, we usually apply a granular subbase to solve this issue. With the granular subbase, we are able to quickly remove the water behind the slab so that we can prevent the generation of the mud pumping effect. So in the summary, the mechanism of the mud pumping is that the movement at the joint due to the heavy traffic load causes the fine-grained soil to go into suspension when subgrade is covered with water. And the increased pressure forces suspension to move upward and out of the joint, thus creating some cavity behind the slab. There are some required conditions for the formation of mud pumping in rigid pavement. First, the soil should have more than 45% passing 0.075 mm sieve, that is a number 200 sieve, with a plastic index higher than 6. And also we should observe some free water between the slab and the subgrade. The mud pumping will usually happen with a very frequent and heavy traffic load. For the design of the rigid pavement to prevent the mud pumping, we need to introduce a sub-base layer between the rigid pavement and the subgrade, especially by introducing the granular sub-base layer. So that's all about the second lecture of the heavy subgrade structure. Thank you very much for your attention. In the next lecture, we will finish all the rest contents in this topic.